Yes, welcome. This is getting to GIST with Backend Services, powering your maps with modern APIs. It's presented by Richard Hargreaves, who's hosting. Murray is also with us as well, and has contributed a fair bit to our presentation. So welcome. So I'm Emma Sylvester. I'm Marketing Manager and helping to moderate today's session. With me is Murray Chapman, as I mentioned, my co-host. He's Associate Geospatial Developer and works closely with our presenter today, Richard. Richard is a geospatial developer with a breadth of geospatial know-how. So the three of us are all part of the team at Geovation. And if you're not already familiar, some stats and figures on Geovation. It's a thriving ecosystem driving national and global geospatial and property innovation. Founded in 2009 by Ordnance Survey, we've grown to over 2,000 members, and in those 15 years have supported over 250 startups. If you're new to Geovation and would like to join, please check out the membership link that will be shared in the chat. Today is about a detailed look at adding location intelligence to backend services. So get ready for a hands-on tech journey into building robust geospatial APIs using modern tools and frameworks. Again, a huge thank you to Richard and Murray who have prepared this session. Richard has a background in indoor mapping and has a keen curiosity in new and interesting ways of leveraging geodata. He's also an integral member of the tech team, which sits at the heart of the Geovation community, providing technical expertise, connection to our network, and signposting development resources to help startups grow. Thank you, Richard. Over to you.
Sure, thanks, Emma. Wow, that's a big intro. Yeah, I'm just hoping that you all want to listen to some techie bits about backend services and APIs. So to be honest, I think we've had a few asks on this session for people to understand, like, okay, we've got geospatial data, we do things in mapping. Yeah, people are sort of ask regularly about API services and sort of how we make geospatial data fit into wider applications. I think if you're part of Geovation, then you're probably interested in serving location data or something like that to a user, and so APIs sort of become a key part of that. I'm going to run us through to begin with, like where does the word like API fit? There's actually some quite like basic stuff I'm going to run through to begin with because I think it's nice foundation for this. I'm going to talk about some off the shelf, like free open source solutions that you can look into in your own time. I'm also going to talk about how Murray's going to step in and talk about how we might serve someone else's spatial data in your own backend services, and then a very basic look at how you might serve your own spatial data. That's hopefully going to look through the whole database process and the API process. It's quite a lot to pack in, so hopefully we can get through it. So API, I mean, if you don't know the acronym, then yeah, that it means application programming interface, and sounds kind of techie, a bit jargony to begin with, but really we're talking about the connection between programs, service applications, many connections. There's not many connections. It can be completely up to the sort of setup of the software you're building. But in reality, if we want to really water it down, it's just program A asking for something from program B. And that program B that's asking for it doesn't really care much about what happens as long as it gets what it expects, which is an interesting sort of theory, I suppose. So that's what an API is. But you might be confused in terms of this session talking about modern backend services. And so where does an API fit? And I sort of grade the box here on a diagram to show what, where it fits. And it fits quite firmly in this sort of, I would say now, dotted line in the way we build software at the moment around backends and front ends. And really, we're just talking about chaining together services that have functions. You can have a storage of where your data is. It can be someone else's storage. It can be your own. I've got a little sort of logo there suggesting a database, but could be a file system. It might have to be a file system depending on the type of data it is. And then you might have some authentication layers, so to have people be authenticated before they access your services. And then you might have a series of API layers. I put API, but maybe that's even too simplistic in itself, that expose and communicate these things between somewhere else. It could even be somewhere else to someone else's API. But in this simple diagram, we're talking about getting all the way through to a user via a sort of front end application. I think maybe the term back end and front end is becoming less and less important these days. I don't think that's a hot take. I think we're really just talking about chaining together to get data that is otherwise hard to see, hard to get insights on, into the hands of people who want it and want those insights. Sort of touched on some software that you might use, but this is just sort of our flavor of what we've gone through in this presentation. There's a lot of words here, but it's actually quite a simple analogy. I think if you are struggling to get to grips with what I mean by API, then let's take even a sort of higher level look at it. I think if you think of a kitchen, so a restaurant's kitchen, you could call that the back end, I suppose, where lots of things are happening. And then the waiter in between might sit sort of sometimes between the back end and what's happening in the front end, serving the customers. Customers never really interact with the kitchen. It all goes through the waiter, and the waiter provides a way to order food. So request data, maybe in this analogy, communicate anything extra, so extra parameters about what you might need about the food or data, I guess. And then it would deliver what you asked for, what you expected. So they're known as responses. And if anything goes wrong, you'd expect the waiter to communicate with you. It's this sort of abstraction between the things that are happening sort of at the lower level in the sort of the weeds of the data compared to what the customer or user expects. This just really talks about one form of API structure, I suppose, RESTful APIs. It's probably what most people are familiar with in terms of building API services. And I had to touch on it really because you're going to see words like get, post, put, patch, delete all over the place if you start building these things. And really they have these definitions. So I think this is actually probably a more useful slide for reference. But we're going to run through today, get some posts on some using with some geospatial data, communicating with a database, so an API in the middle. What's quite nice and quite important really when you're dealing with geospatial data and APIs is you can abstract some of that stuff that is commonly kind of a bit of a pain with map data. Things like coordinate reference systems, maybe tricky spatial operations, or even validating them what you're posting or giving to the database and what you're getting back is what you expect. This is probably simpler with standard form data that doesn't have anything particularly underlying in it that like coordinate reference systems. But with spatial data, if you ask for data and from an API and you get it back in some form you don't expect, then that's not probably going to show on your web service. It might even result in completely wrong measurements and off insights to downstream sort of products, I suppose, that you're serving. So I think an API is kind of essential in abstracting that and acting as a guardrail, I suppose, when you're dealing with these systems. Again, like a really, if you think about that waiter or that analogy, what is he turning up with then, or what's the waiter turning up with when you're communicating data? And we can think of standardly across the internet, data is communicated as JSON, so JSON, JavaScript object notation. And that looks you might be familiar with this. Commonly these things have IDs because we like sort of atomic reference numbers. And then they'll have some properties that help. But this is a little mock-up, I suppose, saying where I am and maybe the preference for my laptop theme. You might see as I go through. I can't deal with white screens. But GeoJSON is sort of an abstract, like to the side, a growth, I suppose, on JSON to add that all important content about the spatial nature of data. You can think of coordinates and types, and there's a really good set of documentation out there for the GeoJSON spec. and it still is probably what most people are communicating data in between their services. There's lots of new and I guess yeah, fancy geospatial data outputs across the internet. We're talking like SPS vector tiles or maybe more modern feature GeoJSONs or PM tiles or something like that. But I think GeoJSON is still pretty common, so I think it was important to raise here. The type here in the geometry dictates what sort of geometry, point being a point, line being a 2 points connected, and polygon being a point ending at the same point to make a shape. And that sort of coordinate list underneath will explain how that's built. And so as that coordinate list is more nested, the more sort of complex geometry you're going to get out of this GeoJSON. Importantly, you can also have similar things as JSON, so properties. So that's sometimes where the most important stuff is. The spatial data might show you where something is and what it looks like and what you can expect, but the properties might be about yeah, all sorts of things that power your systems. Again, like just a high level view of maybe where you might be seeing APIs happening on services if you've used them. This is a really quick demo service of all the canals in the UK. There's actually quite a lot of features here, so communicating it as GeoJSON doesn't quite work as I expect. Like there's quite a little bit of latency with this service. So instead, I had to use vector tiles for this endpoint, and the endpoint looks a bit like this. It's got a Z, X, and Y to point you towards which tile you're expecting to render. And that's a really sort of fast and efficient data format to communicate. And this is sort of what it looks like from a high level. I could show what the file looks like if you open it, but it's all sorts of characters and binary, and it doesn't look very good in a PowerPoint. So not really worth digging into. But if we talk maybe back to GeoJSON, here's another example endpoint of how you would how an API would enable a user on the front end, really. So what does it all mean when it gets to someone? And this here is about a routing endpoint. That this is a custom routing endpoint that I'll go through a bit later. That this takes in like a start point and an endpoint and sends back a route line. And as I've sort of mentioned, it will send that route line back as a GeoJSON. This is a simplified GeoJSON of that route, not the same one. This is just 2 lines. But generally that's what you'd expect out of the service. And so your backend might be just showing information like this, but in the end, it's going to look like this when you're communicating it. Likewise to this, your backend might be showing sort of lots of binary and all sorts of horrible symbols, but when it gets there, it's enabling lovely, fast visualization of canals for this example. Okay, I'll just touch here on some sort of free open source software to be aware of. There's a term in sort of geospatial that's, yeah, I mean, I wouldn't know what I know about map services and using data and being able to develop with geospatial stuff without the term FOSS4G. It means free open source software for geospatial, and it's a fantastic effort, group and community. There's probably more words to describe it than I've listed there. And they cover a wide range of software that can help you do things with map data, do all sorts of things, record it, in this case, serve it, store it. And I just wanted to touch on a few things that you might already be aware of or that you might not. PyGeo API is a Python-based service that you can just spin up, give it in a sort of configuration file, the information about where your data is stored, so that data store, and it will do the rest really. It'll expose it through compliant OGC, which stands for Open Geospatial Consortium standards, which are a really good set of standards that people have come to define how we communicate this data around the world. So that's really handy if you want to get up to speed quickly with serving your own data. Again, Earth Observation API or EO API handles that I've just discussed and more. Really, it's an even bigger project that will serve raster data and Earth observation things like imagery, I guess height data, any kind of sensor that records in pixels. So you could think of like pollution and climate data is quite popular. And then there's GeoServer, which is kind of old school, I suppose, at this point. Lots of people might have been familiar with it. Maybe the first sort of term you sort of fell into when you were looking for an API solution, and you had this funny requirement of being able to serve it on a map. It's a really ubiquitous tool. Um, it just the only downside, I suppose, is it may not be as easy to get spinning up and started with as obvious, I suppose, as some other things that I've listed to the left there. I did want to show sort of what PyGeo API demo looks like. So this is a bit live now, so forgive me if it goes all wrong. But really, if you spin up PyGeo API from scratch out of their repositories, you get big lists of example collections of data they're serving through the example API. So here's one. They're taking large lakes as a data set that's public and wrapping it up and serving it through an API. To begin with, you get a nice visual. Obviously, it's interesting because really an API is this. It's JSON. It's sending all this information around and different endpoints in different ways for different recipes for different people. But visually, it's quite nice to look at here to say that, okay, the data spreads across this bounding box, the world. If we browse it a bit further, we might see what that means. There's 9 lakes here, and I can go in and see some lakes here, and also here, and then I can see information that's sort of recorded alongside that geospatial data. In this case, there's a Wikipedia page and other bits and pieces. And then if I wanted to get the JSON output there, you can see it's exposing it in GeoJSON with some extra bits and bobs to the end. But purely, really, this is standard GeoJSON. And all that is required when you start with GeoAPI is it's the only thing they probably aren't showing here, is a configuration file that tells it, where am I going to grab this data from that you want to show as an API. I played with this with the database, and it is a few lines, and then you're up and running. And all you have to worry about is, I guess, deploying it. Okay. I don't know if I'm ahead of time or behind in time, but this is really the part of the webinar where I want to show some demos of what we've been knocking up, so we can show you how to build these things quite simply. In this case, if we sort of wind right back to the initial diagram I said here, we're going to call the data store a database and not a file system. There's not really going to be any authentication, and there's going to be an API, and we're going to look purely at the responses from that API. So we're not getting into the more visual stuff at the front end. We're just going to be looking at how data started and how it ended up when you get on the API the other end. So I'll just fast forward again. We're also going to wrap third-party APIs. In this case, we're going to wrap Ordnance Survey Places API to help with some location-based searching. The database we're using is Postgres, an open source object relational database, and with some plugins as well. So PostGIS to support geospatial data, and PG routing to support some routing algorithms. We actually did a webinar a few weeks ago on PostGIS. So if you're interested more in like the database side and sort of the lower level part of what you could consider the backend dotted box, then I really recommend checking that out. The API is written in Python, so the language is Python and the framework's Fast API. Really simply, I just want to show you the tree of what the repository would look like. So there's the folders here. There's a backend folder, and in that backend folder, there's an API and a database. I'm actually wrapping this service up in Docker just so I can start it up quickly, and it has all the resources it needs. That's a bit too complex for the reason of this talk, and it doesn't really matter. All that really matters is the API is driven by one file, which is a Python file here, and the database gets initialized, ready to take spatial information, and yeah, and then it's ready to go. Really, it's sitting there waiting for the API to extract information in the way that it wants. Murray, I'll let you take over.
Yeah, thanks, Richard. So yeah. So hopefully you can see this. So one thing that backend API services can be really useful for is if you've got some third-party resource, so whether that's a data set or a search function, as in this case, or even like a large language model or something, and you want to combine that third-party resource with some of your own pre-processing or post-processing. So in this case, we're using something called Fast API, which is just a really straightforward framework for building backend APIs. And we've taken the Ordnance Survey Places API. You can see that they're labeled with this blue arrow. So the OS Places API just lets you supply a free text search text. So it will then return for you all of the relevant addresses across the whole of Great Britain. So it's sort of like a free text search tool. But what we are able to do here with this sort of wrapper API around it is we're able to So we're able to supply not only the query, which is the sort of like the core search term, which is then passed directly into the OS API. We're also able to include these additional parameters, which determine a center point and also a radius. And so what we can then do later on is do a filter on the results that get returned, so that we're looking we're filtering the results geospatially to be those that are only within a certain distance of your area of interest. And this is using two geospatial sort of libraries in Python called GeoPandas and Shapely. And so what you have is all of the advantages of the object-oriented programming in Python and the efficiencies that are sort of built into Pandas and GeoPandas in Python as well. And it integrates, it's quite straightforward to transform between the JSON objects, which Richard was talking about, the sort of standard for web communication, and to convert between those and the geodata frames, which are what GeoPandas use. And so what that achieves is there's a little demo here in terms of what it looks like. So this is what the back end serves to the front end. So if you imagine, you may know that there are two different St Ives in the UK, in Great Britain. One of them's in Huntingdonshire, the other is in Cornwall. And so let's say, you know, your app, you want to search for St Ives Church. Let's say you're a walker and you know where the walker is, and you know their location, and they want to go to St Ives Church. The core base API will give you some results from Huntingdonshire, which is what you want. But then, as we'll see here, there are also going to be 42 results from Cornwall, which is quite a much bigger place. So what we can then do is if we add in the additional parameters, which give you the center point and the radius, that then triggers this geospatial process in the back end and will return a much smaller, much more relevant set of results, only for those which are relevant, only the ones in Huntingdonshire, and we don't get any of the unwanted rubbish from Cornwall. So sorry, that was I don't read into that. Yeah, and it was really, so I just want to emphasize it's a very straightforward, only a few lines of code to apply that. And obviously this is quite a simple example, but there's a lot more sort of like logic and other processes you can apply beyond just a simple search function, obviously. So yeah, that's just one example of how Fast API can very quickly sort of enrich a third-party service. Yeah, I'll hand back to Richard now.
Thanks, Murray. That was really interesting, and yeah, a really good example of wrapping all that information together. Okay, I want to take a little step back as we talk about building this out. So, I mean, this API development here, backend development, it exists in the same space as Murray's been making that wrapper, that third-party wrapper around OS places. What the languages like Fast API and many others as well, object-oriented Python allow you to do is create database migration, so they can also manage your database. I know I guess I learned development in the database. I guess I knew SQL before anything else. I know that's not true with a lot of other developers or other tech people working in tech, and so you can use some interesting tools. This one here is a package in Python called Alembic, which is here on line 8, and it allows you to define how you want your database to change to support whatever you're next going to do with it with your API. So actually, your backend service can do quite a bit more than just sitting on top of your database as you built it and serving what you tell it to serve according to the sort of right parameters. It can control your database schema, I suppose. And also, what's really nice is that keeps a history, a database schema history of how you've built your database in the past. And if you want to take this and deploy the backend somewhere else where the database doesn't exist, maybe on the cloud or in a different location, then you can just spin up all your Alembic migrations, rattle through them. This is just one, the first one I built, which was for a locations table. And all of a sudden you've got a database that looks like the one you've been working with all the time. It might be empty of data, and you might have to do a bit of work to migrate data, which is a slightly different process. But sort of the bones and the skeleton of what the API service is expecting to sort of handle and communicate with, is sitting there waiting. As I ran that migration, actually, I ran this migration, it created a little table. That's an example of a table from a database viewer there called locations with an ID, name, and a geometry. So that's a geospatial table using a geospatial data type in the database called geometry. I then reflected what exists in what I made with the Alembic migration, what exists in the database now, into my main.py file, which is, I've just taken an excerpt of it here in the bottom left, which is showing the object, the model that maps to that. So this is actually not directly related to the database, but it is saying when you communicate with this location model, this is roughly what you're going to expect. So it actually abstracts the geometry back out to, well, I guess it opens geometry back out into latitude and longitude variables. I'm going to show you how we use that little endpoint now. So this is an example of when I first built it. I'm going to show two versions of this endpoint. There was a GET request and a POST request. So the POST request actually comes first because I wanted to populate data. And you can see it's quite simply just a wrapper around SQL to feed the data in the database. But it's really structured. I can't put anything in there. I can put a name, and I can put a longitude, and I can put a latitude. And my API will handle the rest with the database query and turn all of that into a nice geometry that's waiting and sitting in the database. And it will also return sort of that result after it's posted. And then the GET does kind of what you'd expect. It takes that information, it breaks the geometry back out into latitude and longitude for this example, and it lists it out for the user that's expecting the information. I guess the front end that's expecting to deliver the information. So the left-hand side is the GET, and here it's doing the select to break out the geometries that already exist into latitude here and longitude here by using some very simple SQL post GIS functions. And it's then sort of showing in Python how to build that response out here for the locations it finds. So this is actually a listed GET. So it will get everything in the table and give you a nice list in just JSON format in this example, so not GeoJSON. And the post here is doing a very simple insert. Actually, I think the post is actually far easier to read. So I've got a video too, in the pursuit of not doing a live demo. Press send. That send is just a post that's posted it to the database and populated Edinburgh Castle at that latitude and longitude. And then the get is listing that straight back out from the database. I'll show another post here. So if I wanted to, if the front end was able to post a user submitted location of somewhere they want to record, then this is how they would do it. Maybe the way of filling out the latitude and longitude would actually be taking it and maybe on the front end from a user click or a pin mark or something like you might see on other applications, but the name could be something they type as a label, and then that get posted. It sits in the database nicely, and when you get it, you can get all those features back. You could build on this locations get, and actually locations get by ID or by name or by something you'd hopefully be unique, because if you were trying to get just the one response you were looking for. But as you can see, this response is actually a JSON object. It's not GeoJSON. So the reason maybe you might want it to resolve as coordinates rather than that GeoJSON to go directly to a web map front end is you might be using it in something else completely. It might be used in search or something like that. I think if everyone could mute, that would be really handy because I can hear some background noise. Thanks. The next example here. Oh, actually, I think that's just running the video again. Yeah. So the next code example here really is saying, okay, just referencing that it returned JSON. Well, maybe we want it to return GeoJSON. Well, if you're quite familiar with SQL, there's a nice amount of array of functions that can build GeoJSON quite nicely. I think actually this one is probably a little bit more nested than it had to be, taking this from another example I've used previously, but really just that function there, st as GeoJSON, on sort of the middle line here, could communicate the data in the format that we might want. So in this case, the get lists out, instead of in that format that we defined with latitude and longitude, it's going to list out as GeoJSON for each entry. And what that will look like is slightly different here. It's going to call the whole thing a feature collection because there's many features in when it's listing, because we've submitted Edinburgh Castle and somewhere else. And it's then going to have the structure and properties that are essential in the GeoJSON spec. Okay, I think we're rattling through this, actually coming towards the end. I really wanted to dig into something a bit more complex, like, okay, exposing location data like that I've just shown. It's a really good reason for why you probably would not write it all yourself. But although this is a very simple example, if you scale and there's lots of different types of features and there's all sorts of other data types, raster, vector, point cloud, maybe something off the shelf, like I spoke about earlier, would be more robust in the long term. But I think the examples I've shown really help like give a starter for 10 on understanding how we're communicating this information. But in some cases, it is required to have something a bit more custom. So this is using the database again to create routes between start points and end points. It leverages a really good package in Postgres called PG routing, which actually offers up the functions like PGR Dijkstra's, creating the shortest path using Dijkstra's algorithm. And it expects some quite complex SQL, so I wasn't going to go into this too much. But if you're able to use the documentation to create a function that resolves a route quite nicely, then this exists in the database. You can create that, and it's waiting in the database to be used. At the moment, that's not really anything to do with the API. It's, as I say, something the backend's doing to mangle some of the data you had before, maybe in this case, a routing network of Edinburgh, and it will happily give you a GeoJSON route now that you've got a nice Postgres function. So the database can be abstracted really nicely in the API to something so much simpler than that function. You can see we're making a little function in Python here which is really just wrapping around that nested function in the database, which is quite nice and simple. And it's expecting the parameters we saw right at the beginning in the example, latitude, longitude, start and end. And then I'm just exposing that function, get root, to expect to take in these arguments as URL parameters. So in the line of the URL rather than in the body, which I showed earlier. I showed the JSON body for posting. In this case, the getting is asking for the URL, and then it's just pumping those straight into the Python function that's wrapping the SQL function. And I've got a little video of that in action. I also showed the geometry at the end here, which obviously isn't really the aim of this, but here I'm just showing the input variables are the start lat and the start long, and the end lat and the end long. If I press send, that function that I've written in Postgres that's been wrapped in Python purely outputs a nice multi-string GeoJSON for the root, literally just points that make lines. And I'm showing here visually what that GeoJSON could look like. A front end could just consume that GeoJSON and show the line on the map. In this case, we're traveling through Edinburgh in a slightly stepped, laddered way. Okay, as I said, that was me wrapping up, and it just shows a few simple methods of communicating data through your own APIs if you need to. I really recommend looking back at the PostGIS webinar if we have that live. I think maybe Emma can say. But otherwise, thanks for listening. And if you have any questions in the chat or just to me and Murray, then please ask. And also I'm just plugging a couple of Slack channels we have for our community members, Ask Tech Team and Data. They're both kind of used interchangeably. Data is a bit more biased towards asking specifically about data sets, but Ask Tech Team, you can expect to get any one of us who've got a pretty good wealth of experience with these sort of subjects. Thanks.
Does anyone have any questions want to unmute and ask any questions just before we take John's question?
Yeah, excellent. Can I just someone was straight out of the gates there with revisiting the GeoPandas slide. It sort of arose there. Someone's asking, how does using GeoPandas for geospatial processing affect API performance, especially with larger responses?
My experience with this is that probably if you're dealing with a small, you've asked about larger responses. Yeah, the process of transforming into GeoPandas and out again, working from GeoPandas definitely does sort of add some processing time. And the other thing to say is that generally, I think Richard would attest to this, working if you're able to do geospatial functions in the database, those are going to be quicker generally than using GeoPandas. But what I would say is, if what you're trying to do with the data that you get back involves essentially looping through loads of features, doing some kind of logic or a geospatial logic or otherwise on each one, and maybe partitioning the results according to some conditions into two or three groups or something. If you're able to get it into a Pandas or GeoPandas data frame, you're then able to make use of the apply function in Pandas, and the apply function is very efficient and will sort of streamline the process quite significantly. So we found actually what you can do. So we had an issue with slow performance. We were using a different framework called Django. And in Django, and in others as well, you have these things called models, which are basically like objects in Python that reflect or mirror the objects, the rows that you have in the database. And what we were actually able to do is, rather than just working with each model sort of in isolation, we were actually able to put the model objects into a Pandas data frame. And what that meant was, rather than having to loop through each model individually and do the process, you could use the apply function, and that sped it up, made it about 4 times faster. So I haven't done systematic testing on it though, and so yeah. Do you have any other thoughts, Richard?
I think the only other thought, I think it's a really robust answer actually, and quite detailed. But I think performance is also linked to the sort of depend if we're talking about when these things are deployed, then it's also linked to the services and the capacity those services have. So what sort of components you're buying in the cloud really to help you. And I guess most people treat backend services as quite sorry, API services as quite a light layer on top of a data store. But to be honest, if you don't have a database and you're accessing someone else's data, then that might not be true. And so what I'm trying to say is these things will perform better depending on the components you're using, and the hardware that the cloud set up with, but also the database. Equally true of the database, true too. If you've got a beefed up database with lots of memory and lots of capacity, then that can help too. One of the advantages of databasing that I like is things like indexing, which really do a good job of speeding up queries, geospatial queries. So geospatial indexing helps the problem of the intersection problem of trying to intersect one thing with a million things or a million things with another million things. It just resolves in a really efficient querying process. Yeah, I hope that explains it. I've just seen Jack's question. Could you go over
Yes.
deployment options? What is the best way to be scalable? We might not be the best people to actually be authoritative on this, but I think the best way to be scalable, especially and not get burned by cloud costs, is to build for your need right now. I think that's actually maybe a bit of an underrated thing to think about. So if you don't have many users right now, and maybe you don't have that much of a processing load, then make sure you get cloud resources that suit that, because then you can know really the cloud providers, all of them. Azure is what we use quite commonly here in OS, but we've had experience with Google and AWS. They will all tell you quite openly this isn't quite working in the way you want it to. Or this is overloaded or underloaded. They don't tend to like to do that if you have already gone for a service that's too big for your solution, because I guess that just is quite a good way of making some money. I think the best way to be scalable with data is to ensure you have those clever things like indexing involved and really neat and well structured database architecture, if that's what you need. Otherwise, some other good options can be actually using sort of file stores. Web buckets, I suppose, like Amazon buckets. So I guess there's another one in maybe there's different names, Google Cloud Storage, or Azure Blob Storage. These things are far cheaper options on the cloud, and these days the backend services are really capable of communicating with them fast in different ways. So that can be a really good alternative if you don't want sort of maybe the more premium managed database services. Probably hasn't given you an answer, Jack, but sort of spoke to my experience on the topic. Mario, I don't know if you have anything else to add.
I don't think I've got anything more profound to add to what you said. Can we share Postgres tables online easily? It's an interesting.
It's an interesting one. It depends what you mean by share. If you mean multiple access, then as long as the sort of database that your table is in is with a cloud provider of your choice, then you can have loads of users and roles and access and lots of different access capabilities as well. So if you've got maybe some people in your team you wouldn't want to have as much access to parts of the database as others, and you can manage that. And it's really easy and clear really with creating roles with passwords and letting people into database. If it's locally and you want to send them between people, then traditionally I use database dumps. So you can use PSQL, which is a command line tool that comes with any Postgres installation, and you can send those around. And basically, they give you a completely unreadable output of the database in pretty much binary. And then when someone receives it, they can restore it and get your database that you had in your, and it will be full of the data and the schema that you were working with. So dumps is the most robust way. They're literally called .dump files to communicate data with dumping and restoring.
Is OGR to OGR relevant here, Richard? Would you say, or would you say PG dumps is sort of superior?
I think if you're looking for, so OGR to OGR is a really good shout. So OGR to OGR is a GDAL tool that helps you load geospatial data into pretty much anything. Not even load really, just ETL. So change its format from one thing to another. The only thing you can't be sure of is that it's going to end up in a database that looked like the database that you had. So the good thing about dumping and restoring is you literally get a carbon copy of the database you had on someone else's computer. So you get the schema and just the schemas that were in that dump, and it ends up on someone else's. The only downside of OGR is you can move spatial data around nicely, but when it gets into the database in a Postgres table, if you haven't done it exactly the same as the last person did it, then it could which is fine if you're using the defaults, right? But if you're not, then it could look different. But it's a really handy tool. GDAL is probably the second or maybe the most important geospatial library. Yeah, GDAL. There's lots of tools on the GDAL website.
We've also got another in the Q&A chat. Is it best practice to get an API to validate geometry integrity? Example, tank valid, etc. When posting features to a data set, is it capable of providing a response to the user if features are invalid, or would this need to exist elsewhere in the system stack? Thanks.
Yeah, James, it's a good conundrum actually. Like it could exist. I would say that this stuff could exist in the database in and of itself. That if we're talking about when communicating data to databases, then it can exist in the database. There's lots of ways of doing database architecture with foreign keys and data types that basically stop things from going in that aren't supposed to be there. But if you're talking about moving data just between APIs and services, maybe the front end sends something back to the API that isn't put in a database, but it's still in the wrong format for another thing that's happening, another geospatial operation or something like that. Then we've typically used JSON schema. We really use it. We use it quite a lot here, and it's really handy. It allows for effectively a crib sheet or a set of rules written in JSON that tell you what to expect and what to send, and it will tell you exactly what's wrong. And it's a really handy package. I think it actually exists in all sorts of languages. I mean, we've got familiarity with it in Python because that's our sort of core capability, but I think it's a very common tool. And you can define all sorts of things. But in terms of GeoJSON validation, some of those objects as well that Murray was speaking about, those objects in your Python framework like Django, or there's probably one in Fast API, can also provide validation. So there can be validation, as you kind of see by this answer, in all levels of the stack. If my recommendation, if you are dealing with sending stuff between databases, is to try and very much at the start define in the database the rules of each column. Those little things are important when you're building a database that you kind of don't think are when you first start. Like, is it a varchar with 10 characters or 11 characters? Well, if you want to stop someone sending something too long, then you probably should care about the character count. So it's interesting. I've made many blunders not caring about those sorts of things and realized that it's best to start from the beginning, where the data is stored.
And I don't know whether JSON schema in the database allows for this, but you could certainly in the back end do additional validation to sort of, for example, check that the geometry isn't empty, or to like check if you're expecting a single polygon but you get sent a multi-polygon, for example. You can validate on the shape types. So like it would still pass an ST valid test, but you could do additional custom tests as well beyond that.
Yeah, and another really good capability of GeoPandas as well. You could do that both with data types in the database, but in the GeoPandas, in that sort of middle layer as well, GeoPandas could say like, no, that doesn't look quite right. I don't want it to look like that. Or maybe you'd use Shapely, Murray. I'm not sure. I'm not too familiar with it.
Yeah. So Shapely is when you're dealing with an individual shape. GeoPandas is if you're dealing with a whole column of shapes, basically. Yeah.
I think we're sort of ready to wrap up. Just Murray, Richard, a big thank you very much for hosting the session and sharing practical examples of modern APIs at work. I'm so relieved to know that they go beyond actual pandas. So thanks for some of those restaurant analogies. That's brilliant for someone like myself, but appreciate the technical detail you've gone into today. I hope others have found it informative. So, and going back to our participants, a sincere thank you for attending and joining us and for your input. And just to close, really, don't forget to check out our membership link if you're interested in becoming part of Geovation. And last but not least, and really, really important, is to ask you that you share your feedback before you go. And we hope you join future events coming up in the new year. So thank you very much, everyone, for joining. Bye then.
Thanks, everyone.
Thanks.
Thank you.